This video is about the Renesas X9C103 digital potentiometer, and specifically about how fast you can change its wiper position and still get good results. Digital potentiometers are simple but interesting devices. You might be tempted to use them for something like signal generation, but this makes more sense if the potentiometer can be changed quickly. Spoiler alert, it can't. Here's the device's datasheet. I have the 10K version. I read this datasheet to find out about speed, but the datasheet wasn't very clear, so I tested. If you're not familiar with digital potentiometers, here's a block diagram of the X9C103. It's basically a chain of 99 resistors connected to the VH pin at the top and the VL pin at the bottom. There's a wiper pin, VW, that can be connected to any point between the resistors by turning on one of the transistors. In a stable state, only one transistor is turned on at a time. An up-down counter controls which transistor is turned on. The control signals on the upper left allow the counter to be incremented or decremented. It's also possible to store the current counter value in non-volatile memory so that the value is restored on power on. Note that you can't put too much current through these things. The timing diagram shows how you use the control signals. Basically, you set the up-down direction pin to what you want and then bring down CS. After that, you toggle the ink pin down and up as many times as needed to reach your desired counter value. The question is, how quickly can you do that? T-Psych, TIL, and TIH suggest that you can toggle ink in as few as 2 microseconds. That's pretty fast. But VW says it can take the wiper up to 100 microseconds to respond to each toggling of ink. That's pretty slow. So what's going on? The datasheet actually provides a clue. It says that the wiper changes using a make-before-break scheme, and that if you change the counter too fast, more than one transistor might be on at the same time. This would effectively change the pot's total resistance for a little while, and could easily mess up your use of the device. So I decided to test both fast and slow toggling of the ink signal. Here's my setup. I wrote trivial software for an ESP32 to control the pot, and I connected VH to 5 volts and VL to ground, so the voltage on the wiper is controlled by which transistor is on, that is, by the counter value. Let's test. This is the Scopy oscilloscope application. The orange signal is the digital potentiometer's increment pin, and we'll be triggering on it, in particular on its falling edge. The purple signal is the voltage coming out of the wiper pin. So when we're at position 0, it will be 0, and when we're at position 99, it will be near 5 volts. The software is set up to cycle the increment pin at the maximum speed, and that's 2 microseconds as allowed by the datasheet. Let's see what happens if we try to go from position 0 to position 99. So we'll do a single trigger and enter 99 to the software. And we can see that the output voltage does go from 0 up to its maximum value, but it doesn't do so evenly at all. It's often below where it needs to be on a linear curve. The good news is that it makes the transition in 406 microseconds. The bad news is that the output is very irregular, and that's the problem. So we can also watch it go back down to 0. So we'll enter 0, and we see a similar problem there. So next we need to try this with the software set to take 100 microseconds to toggle the increment pin. That's the amount that the datasheet says is required to be sure that the signal is going to be nice and smooth. Now we're reconfigured for a test with 100 microseconds of cycle time for increment. And let's do a single trigger and go from the top to the bottom. And we can see now that the voltage change is very smooth, just as you'd like, going from 0 to a near 5 volts. But the downside is that this is taking about 10 milliseconds, so it's very, very slow. And just for fun, we can see it go back down to 0. So when we run the part very slowly, the signal change is very smooth and nice, but very, very slow. I'll end this video here. I hope it saves you some time if you are thinking about using this kind of digital potentiometer. The ESP32 software is quite trivial. If anyone wants it, let me know in the comments and I'll put the sketch onto GitHub. Thanks for watching.